So hi guys, we're doing our presentation about the steering and braking mechanism and also the guideway. I'm Chin Ming.
Tango.
Jeffrey. Alex.
So why do we need a brakes for the bogie system? Now it's a simple question, but yes. Brake is very important in preventing collision, crashes, emergency cases, and also it controls the speed of the moving vehicle. The steering mechanisms also ensure that the transition during switching sections is more smooth, easy maneuver. So over the research, I think that this brake is the best option for the bogie system, the quarter scale, because it has really affected braking mechanisms. According to the statistics showing that front disc braking annually prevent like 10,000 accidents, which results in like 64 fatalities and 5,700 injuries, and would cost like $32 million in damage for the property. So what's this braking? This braking is basically tire brakes that use calipers to squeezes the brake pads against the rotors, as you can see right here. And basically the pads retard the rotation of the shaft, so it slow down the vehicle. This brake uses the calipers, and there's two tire calipers are there. One is the floating calipers, and the other one is the fixed calipers. Fixed calipers, they use two or more pistons. So piston is the part inside the calipers is on the other side, so you can't see it over there. But basically, what the piston does is when you apply brakes on your vehicles, it transfers it injected the fluid or the oil into the hose, and it goes through the piston that being pushed against the brake pads, and it's created the friction that slow down the rotations. The fixed caliper is more expensive compared to the floating calipers, and they use it more for like sport cars or like really high performance vehicles. The second choice is the floating calipers, which is more popular among like regular cars, and it's less expensive. So floating caliper, they use like only one piston, and basically the piston is houses inside the calipers, and it's pushing the pads against the rotors, and also it's pulling the caliper bodies to the side, and there's also a brake pad behind inside the calipers bodies, and then just push the two brake pad pushing evenly onto the rotors, and slow down the vehicle. The brake pads is usually made out of metallics or semi-metallics materials, and the pistons are usually made out of plastic or aluminum. So the main advantage of these brakes is that it's really good in heat transfers compared to like drum brakes, which all the components are housed within a drum. When you brake, it creates a lot of heat at the byproducts, and when there's all the heat, it affects the performance of the components, and it makes the brakes being less effective. But for this brake, the rotor is exposed to the ambient air, so when the friction created a lot of heat. It's being released to the air, and also the designing of this brake is more easy to maintain. It has self-adjustments, so there's less cost to keep maintaining the parts. And also for the effective brake hard brakings, like for the scenario where you go down a steep hill, if you use this brake, it's more effective because it can take in a lot more heat and disperse the heat to the surrounding, compared to like the drum brakes, where I said that if the heat is building up a lot inside the components of the brakes, it's when you're trying to brake, it's gonna fade it and it's gonna be really dangerous. Also, the designing of the rotor is circular, so that it's water repellent. So when you go over to like the water surface where you have a lot of liquids, can stick it on the rotors, it's gonna be roll off easily. So it has the wheel to perform better. Also, there's two types of these brakes that they use airs, which is the one shown right here for train. Air brakes is more for like heavy duty vehicles like trains, large size trucks, but also it's take a lot more spaces for the components because all the parts are really big compared to the hydraulic brakes. It's much smaller components and it's less expensive and it takes less room for the functional, spatial functional needed. That's it.
Right, so I'm going to talk about the steering mechanism. So as you can see in the picture, this is the current mechanism that last year's team worked on. And this is like the CAD design of last year. So at the second week of class, we observed the bogie, the steering mechanism. The advantage we found is it works properly, and the guide wheels attached to the other rail, so it will change like reels according to the direction the pocket wants to move. But however, when we observe steering mechanism, we notice like a few faults. First of all, the mechanism operates pretty slow and pretty sluggishly as well. If we would implement this design in the real world, it will not be really time efficient because it will cost because there are many parked cars that will be traveling on the same network, and that will cause major delays. So also we noticed that when the bottom lanes, the switches rail, only one side of the wheels they are attached to the rail, but then you have three hanging wheels on the other side. We want to try to fix that. And also, this current steering mechanism has two actuators, electric actuators, that operate simultaneously. That operate both the upper linkage and the lower linkage, but it may lead to mechanical failure if those two actually just don't sync together. And we try to instead of having two actuators, we try to implement only one actuator to prevent mechanical decrease the chance of mechanical failure. So the following. We have the following specifications for the quarter scale model. So you want the steering mechanism to activate about 1 second. And we want to have a braking system that gradually slows down the vehicle to prevent overheating components. Assuming the model will travel about 5 miles per hour, that's what we're trying to aim for. We also want to reduce the vibration levels when switching the tracks to have like a smoother ride. We also want to generate low noise levels.
So I'm going to talk about some of the challenges we are facing in our project. So the first challenge is to redesign and simplify the existing design of the steering mechanism. So in an old design, there are for the steering mechanism, it consists of upper and lower guiding wheels. Both the steering wheels are controlled by 2 actuators, but we want to simplify the design by using 1 linkage to connect both the steering wheel. And the second challenge is to install a braking system on the bogie. And then the third challenge is to look for some of the products on market that we can use on our 1/4 scale model. And the last challenge is to configure some of the tolerance of the design and decide what kind of material that will be used on a 1/4 scale model. Yeah. So here you can see this is some of the product that you can find on the market. And this is a brake system on a 1/5 scale model RC car that is gas powered, manufactured by Tim Lucy. And you can see that this is a disc brake, and that's a brake pad. It's a dual system, and the diameter for the disc brake is around 2 inches. You can see the brake system is controlled by a servo using a linkage. There's a leverage that pushes the brake pad against the rotor. However, there is some more work that need to be done. For example, friction material needs to be added on the brake pad, and we need to make a special hub for the rotor. The hub can be made by CNC or milling machine. And here we can see this is a radio control servo made by Futaba. This is a high torque one. Again, this can be found on 1/5 scale model, and we have decided to use a high torque servo for both the steering and braking mechanism. And this high torque servo is really powerful, and it needs an external power source, usually like a 7.4 battery, and it can deliver a torque of 19.2 kilogram per centimeter. The servo can turn 60 degrees within 0.2 seconds. And although we are not building a full-scale model, but we have come up with some ideas that we can put on a full-scale model. For example, you can see this is a drum brake, and a disc brake you can find on a regular automobile. But our team would prefer the disc brake because structurally this is more simple. It only consists of a caliper on the rotor, and they are easier to be modified. And we are thinking about we change the design on the caliper so that we can put a pneumatic actuator instead of using a hydraulic power for the caliper.
So yeah. So the current actuators installed in the current steering mechanism are electric actuators, but so because it operates slow, so I propose you should use a pneumatic actuators, which basically converts compressed air to mechanical motion. Pneumatic actuators mainly consist of the cylinder, piston, and valves. The reason why we should use the reason why most use kinetic actuators is because the force and speed are easily adjustable and they're independent from each other. Unlike the electric actuators, the speed and all can, once it's set, you have to like change the motor and all that stuff. And the kinetic actuators are actually simple in design, so we want like to have simplicity in our design. Also, actuators, the cost of the components are low generally, and also they require minimal maintenance, and they're also quite durable. Also, the kinetic actuators are pretty safe in flammable areas, hazardous areas, and they are really accurate. However, some disadvantage is that they do are prone to leakage, and we must when we choose one of these actuators, we need to really size them really correctly to our needs. So the goal of our project is to build a quarter scale model of scale down our full scale model to about a quarter scale, and we try to improve the modified existing design of the steering mechanism and try to replace the current actuators with pneumatic ones. We also try to develop a mechanical lock system to keep the steering mechanism engaged to the guideway so it won't has no chance to fall off. So these are our team's responsibility. All of us, me, Tang, and Jeffrey will work on the steering mechanism, try to refine it, try to redesign it so it will work more properly. Tang will research more into detail about braking technology, and we will also assemble and build steering wheels and braking system. Jeffrey will try to look for more components for the quarter scale model, and also design a braking system for the scale model. And I'll be doing more research into the actuators, and I'll also will perform more necessary force analysis and calculations. So this Gantt chart is approximate. It's not. It is approximate. What has to get done by a certain date within a certain period.
All right, I'm going to talk about the guideway. What is the guideway, or why is it important? Well, unfortunately, without a guideway, you won't be able to move. Our pod car can't fly, so we need a guideway to support itself with its passengers. And what are our requirements for the guideway? Our main requirement is that our guideway comes down and up at 17-degree angles. Now, why is this important? It shows that we are not limited to the ground. It can show people who are interested in our project, investors or officials, that we can work throughout multiple different types of city layouts. Let's see. Yeah. Oh, we can also build above and under structures, so we're not so limited to, like I said, the ground level. Yeah, just more of that. Here we have some similar methods that are being done. This is the TubeNet transit cards being developed in Beijing. Right now it's a concept, but it's very similar to our model in the sense where there are solar panels on top of the tracks. And the difference with this model is that it has metal frames that connect the solar panels to the rail that supplies power to the pod car. To the right, there's a city layout with the tracks. Here you can see multiple stations, and what's kind of neat about this layout, there aren't any street stations. They all go into residential houses or buildings. That's interesting. An existing similar method we have today is the Morgan Trail PRT. It has 5 stations, 73 cars, and just like the one in Beijing, it's a supported vehicle system. Ours is a hanging supported vehicle system. And as you can see from these tracks, they can move through angles, gradual angles, very fine. That's something we should be able to do. We're going to stick to the previous year's designs just because they did a lot of work, and it's when I mean we're going to stick with it, we're not going to change the cross section, the post, the frame, or any of the main structure. Yeah, I read in the designer Keith A. McKenna, he designed the composite wooden framing. He said any altercation to the system will require a full redesign, so we need to save time by doing that. Some HSV tracks are common in roller coasters. You've seen this before. What's cool that they can twist and turn. There's no switching mechanism on board these. I don't think I've ever experienced one of it switching. So we need to be able to do that. So some of the functional specifications, we'll be keeping the last year's track design. We want the incline to be 17 degrees. And we also want to fulfill other team requirements. So we're going to be considering other teams' needs. So I know I said we shouldn't change much, but we still need to kind of change a little to accommodate. We want to focus on a complete track rather than a track with no end. I think it'll be better so we can demonstrate the angle as well as switching and an easy reset. It'll come back to its start position rather than pushing it back like we're currently doing right now. There's a challenge with this, however, as opposed to having just a simple track, which is a fine idea. It demonstrates what we need to do, but it's just real simple, and it's nice to have something nice to look at. The challenge would be comparing cost, time, and functionality. There's a challenge that I've talked to with the suspension team. The incline cannot be a sudden drop. It needs to be a gradual drop to avoid collision from the pod car to the rail. So the suspension team will have the pod car constantly upright. You don't want it to hit the rail, so we need to keep that in mind. There's also a challenge with the wayside team. Where would they supply the power from? And the idea that I looked at from the previous reports were wiring the rails so they'll be in constant contact. Another thing we discussed were just completely changing the propulsion system from the middle to the outside. That way they can run a rail right through the middle. It might be easier that way to supply power. Alright, well, the goals for this project is to make a functional support intermediate structure for the pod car, and it needs to demonstrate inclinations and declinations. We also want to fulfill other teams' needs, and we want to make it so it's easy to disassemble, reassemble, and move around. This is the Gantt chart, and one thing I want to just point out is the redesign based on everybody's input. I want to do that as soon as possible so I can get in contact with the previous designer and see what insight he can give me on what we can do and what we can't do, or what's reasonable given the time we have. And if you guys can do that as soon as possible, that'd be good. Thank you. All right, let's see this photo. It's over.
Questions? Comments?
Yes.
How does the small scale currently break right now, or does it have breaks? You know, so maybe
Just small scale.
Yeah.
No,
You mean the one we're working on, the intermediate scale?
You're talking about a servo motor as a disc brake on small scale.
small scale.
The quarter scale.
Quarter scale.
Any other questions, concerns, comments?
Any comments, things you thought they did well on in the presentation? Feedback?
Pretty good.
What did you guys do very well? This breaks another mass option. It's good that you're trying to reduce the complexity of those components. Comments? Okay, so get the first shot out of the gate here. So it looks like maybe there were sort of 3 presentations embedded in here. Is that
2?
kind of
Yeah, 2. Yeah, you're right.
Stereo.
right?
Yeah.
So I think it would be strengthened to make that clear sort of at the beginning. You know, we're going to present first like this part, and then we'll switch to the next part. It wasn't clear. I didn't know if you were jumping around there. And then your slides were in that AE format. So you nailed it pretty well, okay, with assertion at the top, really nice graphic that you kind of worked through. The other slides, did you guys not see the AE method? Did you not look at that because they were not in that format? Right? Assertion, sentence, I didn't see any for those. I saw a lot of bullets. Yeah, so talk to Alejandro about how he did his and work yours up for the next one. Let's see, Tom. I think you had some great graphics on the